Example 8.4, you have landed a job in a movie studio or movie industry as a special effects engineer. The script of the movie to which you have been assigned calls for a square flag, which, which originally hangs straight down from a horizontal flagpole to swing up and hang at an angle of 37 degrees from the vertical, as though lifted by a ghostly wind. To create this effect, you set up a uniform vertical upward magnetic field and run a wire around the entire perimeter of the flag. When you connect the wire to a voltage source, a current flows in the wire and the flag levitates. The flag has a side equal to 1 meter and weighs 60 newtons. A. Draw pictures and write out Newton's second law equations. B. Determine how much current must flow in the wire for the flag to levitate to the desired angle. So let's draw a good picture because this may be hard to visualize. There is a flag hanging from a horizontal pole / rod. So I'm imagining a picture something like this. Here's going to be my pivot point or where it's connected to the wall. And then I'm going to have a flag that's, let's say, something like this. So right here is the actual pole that's holding up the flag. So now if I look at this flag, let's say it does this here, we could probably, since it seems like it's a scary type of situation here, we could imagine that we want to maybe draw an image of this thing. And then, of course, we have to give it teeth. That's the flag that you're seeing on the set. So what we want to do is the goal here is to levitate this guy. So what do I mean by levitate? So if I think about levitating, this is, you're looking at this thing straight up, but an angle that will be better is if it's at a side of the thing. So the goal is to make this flag levitate. Upwards to make it appear to float up all by itself. Let's say this view might help to visualize it better or the situation better. So if I start drawing things at an angle, I imagine that I have something like this. I'm going to have my pole, and let's say that it goes something like this. And then I'm going to have the flag coming down. Yeah, that's the flag right there. Now, in order to do this, what I have to do is that I'm going to immerse this in a magnetic field. And I'm going to call that the Z direction. So now what I'm going to do is that I'm going to wire this with the loop current. And let's say just to get the same type of scaling correctly, I'm going to take this right here and I'm going to, now I imagine that this angle right here is the vertical that we're going to measure. And so now the flag here is going to come down something like this. It's going to sort of float up, levitate. And the way we do that is that we're going to run a wire all the way around this guy so that it forms a current loop. So we're running a current loop because we know we have a magnetic field in the z direction that looks like this. So again, this is the current that we're flowing. And we want to levitate this in such a way that it increases its angle from 0 to 37 degrees. So now we have a current loop that's immersed in a magnetic field. So now we have to go from here. So from our lecture on current loops in magnetic fields, we know that the net force for translational motion is going to be 0, which means that its center of mass is not going to move, while the net torque initially is not going to be 0, which initially causes angular acceleration. It causes a rotation until equilibrium is reached or established. Now, let's draw the free body diagrams, right? And the torque body diagram for the flag. Now, because of what's going to happen, I think we should first look at the magnetic forces, and then from the magnetic forces, we'll then draw in the rest of the forces just to be clear. So we're going to start with the translational in 2L. In other words, we need to draw the free body diagram. So as I said already, let's first identify the magnetic forces on the current loop. Since the current loop is angled, we need to look at each segment. Let me be careful. Each wire segment to identify the magnetic force or the magnetic forces. So let's set up a coordinate system. We've already identified that the z direction was going to be the direction of the magnetic field. So we know that's that. So now I have a couple of choices in picking what is the x and y direction. So I'm going to pick the x direction coming out, which then forces this guy to be the y. So note that each of these directions are the positive directions. So that's positive, that's positive, that's positive. Anything other than that is in the opposite direction. Now, what I'd want to do is that I want to go ahead and look at this flag again, but let's look at it from a front view, because we're going to have to go from the front view to the side view to really get a feel for what we're talking about. So here's my flag with my pole, and this guy is going to come down all the way down here. So what I'm seeing here is that I have this wire segment. It's going to be going in this direction. So I'm going to call that IL1, that segment. And then if I just start to do this whole thing all the way around, now I'm just going to keep writing in my segments. And the obvious one is call that IL2, IL3, and this will be IL4. And once again, we have a magnetic field that's coming through this, but this is deceiving because we don't see the angle of the magnetic field. That's where we have to then start with the angled version of the field. So the easiest for two of, no, for all the sides is the side view to get the magnetic force directions. So let's focus on length 1 and 3. So if I look at this here, so I'm going to focus on lengths I1 and I3. So let's focus at I1. So if I'm looking at this, you could see here that it's moving upwards. So then I'm going to go, okay, so let's say here's my wire. And it's going to be going on. And if I look at the current, if I look at that, I'm seeing here that this guy is climbing uphill. But the magnetic field is pointing directly upwards. So if I look at this, I need to break these guys into components. And what you're seeing here is that I have one component, oops, wrong arrow direction, which is then going to be IL1 perpendicular. And then I'm going to have another component, which will be IL1 parallel. And what I mean by parallel, it's parallel to the magnetic field. So right away, we can see here that the guy that cancels out is going to be that guy because it's parallel. So that immediately tells us then, from the right-hand rule, I have I hat perpendicular to BZ. That tells me that the magnetic force for this wire, oops, is going to be FB1 in 2. Now, if I do the exact same thing for wire 3, then I'm going to be drawing something like this. But now the current is coming down instead of up. And you can see here that because there's a switch in direction, we expect the force to be in the opposite direction. So if I play the same game as I've done already, I could see that I can break up the this guy into components. So I could see that I'm going to have a component that goes down. That's going to be I3 parallel. And then I'm going to have a perpendicular component, which will be IL3 perpendicular. And then you could see here is that I have a magnetic field that's going in that direction. So right away, the fact that this is anti-parallel, that's not going to contribute at all. So I only have this guy right here. And as expected, we're going to get a switch in the magnetic force, and that's 3. So if I look at the sketch above here, I got to see, so what direction does this mean in the picture above? So in the sketch above, it points to the right in the y direction. And the same thing up here, this guy, it points to the left in the y direction. And I'll draw the whole picture out here in a moment. Now, let's focus on the other 2 lengths here. So now we're going to focus on lengths I2 and I4. Now, picture-wise, this is a much easier picture because if I look at this, even though it's angled, the picture just tells me whether the current's coming in or out. So if I look at this guy, here's what I'm seeing. I'm seeing that I have this guy again, but the length that I'm showing right here, this right here, is current. What did I call that current? I don't remember. I think it's I2. I'm going to call that IL2. And if I look at the magnetic field, you could see immediately that the magnetic field is already perpendicular to this. So if I look at this guy, the right-hand rule then just tells me this, that I have my current coming in like this. I have my magnetic field going like this. Therefore, the right-hand rule tells me that I'm going to have a magnetic force going to the left. Now, if I repeat the same process for the length of 4, then it's now going into the page. Right here, and that's going to be the current I4. Again, my magnetic force, my field is in that direction. So if I play the same game as before, where I have this guy here, my magnetic field, now my magnetic force has to be in the opposite direction. So in other words, I should have drawn this in the other direction so that this comes out cleaner. So this will be the magnetic force for wire 4 when this is IL4. So now I have the whole thing. So let's put this all together. So now I want to draw all of these magnetic forces. So if I look at, again, the side view here, I'm thinking something like this. There's the edge of the current loop, the flag. And what I'm seeing is that I'm seeing this. I have a magnetic force FB2 right there. I have this magnetic force FB4 going in that direction. Now I have two forces that are coming in and out. This one will be, how did I label them? This is B1 going in, and so therefore that must be B3 coming out. Those are the magnetic forces. Or another picture that I could draw here, if this is clearer, if I come over here and I just copy this and bring it down, I could draw the picture that just says this instead. I have a magnetic force that goes this way, which is FB1, one that goes FB2, FB3, and then finally FB4. So when I'm looking at these guys, you could see that if we start to look at torques, you could see that 3 and 1 will not produce a torque. The only ones that can produce a torque is a combination of 2 and 4. So now that we got the directions of the magnetic forces, let's now include all of the forces. Now we draw a free body diagram that includes all of the forces. And I'm going to do this as a side view. So if I copy this guy right here, then I just got to add them. So the first thing, I'm going to have to make this a little bit more clear. So I'm going to take this force and I'm going to move it over here. I'm going to take this force and I'm going to put it on the other side, but it's still there. So the first thing that we should see here is that the flag must have weight. So it has to have a center of mass weight right there. And the other thing, the pole is being held. So the way it's being held here is that part of it is supporting the weight, which I'll call that normal 1, and part of it has to keep it in, which I'll call N2. So once again, we had already defined our coordinate system someplace. Here, we could draw this again really fast. I believe that we set our coordinate system to be something like this. So if that's the case here, now I can apply Newton's second law. Now these guys are in static equilibrium. So if they're in static equilibrium, then we know that the net force in the x direction is the direction of 1 and 3. And you could see right away that this says FB3 minus FB1. These guys have to be equal to 0. Now, I have my y components. So my y component says that I have 3 forces in the y direction. And according to this, remember, going to the right is positive, going to the left is negative. So then this should be positive FB4. Then I'm going to get minus FB2 plus the normal force, which will also be negative, and that has to equal to 0. And then finally, I have the net force in the z direction, which then says that I have positive N1, and then I'm going to get a negative mg, and that has to be equal to 0. So now we're on to the rotations. And I'm probably going to want a picture of this, so let me copy this picture and then just have it. So now let's go on to the rotations. So the rotational, Newton's second law. Since the pivot point is where the flagpole connects to the wall, there is no torque created by the forces at the wall. Okay, since the pivot point is where the flagpole connects to a wall, or it could be something else, there is no torque created by forces N1, N2, and the magnetic force F2B. So if I look at this picture, what am I actually seeing here? So if I look at this thing, what I'm seeing is this. This thing is going to have to rotate about here. So this is the pivot. So that means N1, N2, and N4 have 0 lever arm. So they're gone. They're not going to be there. Furthermore, forces FB1 and FB3 will never cause a torque. So I don't have to worry about them either. So these guys are also gone right there. So I only have two forces that can cause the torque. In other words, only forces mg and FB4, which I'm now going to define as just FB, will cause any rotations until the flag reaches equilibrium at 37 degrees. So in this situation, here's what we're seeing. This guy, it has to cause a torque that's going to be counterclockwise. On the other hand, this guy is going to cause a torque that's going to be clockwise. So according to Newton's second law here, we can then say that the net torque has to be the torque due to the magnetic force minus the torque due to mg, which means then that we have a lever arm for the magnetic force minus the torque due to gravity times its force. So these two guys have to balance out because now it has reached equilibrium. So now we need to calculate the lever arms. We need to calculate both lever arms. So the first thing that we'll focus on is the magnetic force. So we're talking about the magnetic force lever arm. So if I look at this, I'm going to have this scenario. I have my pivot point right here. And so that means I have this guy. So if this is my 0 point, then you could see here is that I'm going to have my magnetic force right here. And then I have to have my lever arm that comes all the way from the point of rotation to where this is at. And this is RB. And this guy has the full length of the flag. But note, we know something about the angle. This is 37 degrees. So the first thing that we need to do here is that we need to bring the tails together. So if I bring the tails together, you're going to see here is that I have a magnetic force like this. And I have this guy right here, which is RB. Now, when I'm looking at this thing, what you're seeing here is that this angle right here, this angle is what is 37 degrees. So that tells me that this angle here, which will be 90 minus 37, is then 53 degrees. So if I now look at this thing, this is the same as drawing it like this. I only care about the perpendicular component. This is going to be RB. And then I'm going to have, by the way, that's RB perpendicular. This will be RB parallel. And what we mean by parallel, it's parallel to the magnetic force. And as we already know, this guy will not contribute to the torque. And this guy then is L sine of 53. From the right-hand rule, R cross FB, I'm going to have a torque that's now going to be counterclockwise. Now, if I look at the other one, this is the mg force lever arm. And in this situation, gravity does not operate at the full length. You know what? The picture is different. So let me redraw this again. Gravity is acting here at the center of mass point. So we can see here is that this guy is mg. Now this lever arm, you could see that because it goes to the center, that's going to be rg, has to be half the length right there. But the nice thing here is that, look, this angle here is 37 degrees. Now I'm going to bring the same thing, these tips together again, just like we talked about before. And so if I do that, then I have this picture. I have my green mg going down. I have my vector r coming in this direction. And you can see here is that this angle right here is 37 degrees. So in this situation, breaking these guys into components, I then get this. I have a component that's parallel. And I have a component that's perpendicular. And as we've already said, the parallel component will not contribute. As a consequence, I'm going to get R times this. This is going to give me a clockwise torque. So now, if I put it all together, we could then say the following thing. So if I now apply Newton's second law for rotations, we then say that the net torque will then equal to the torque due to the magnetic force minus the torque due to gravity. And this guy is 0, which then implies that I have the perpendicular distance must equal the perpendicular of gravity distance. And putting this all together, I'm going to get L sine of 53. And then this will be the magnetic force is IL times B. And then this guy will give me 1/2 L sine of 37 times mg. That now we can finally solve for the current. And we get that I is then going to be 2LB sine of 53. And this will be mg sine of 37. And then I'm just going to put in all the values. So we know that the length is 1 meter. We know that the magnetic field is 0.60 Tesla. Then we have the sine of 53. And then we have a weight of 16 newtons times the sine of 37, which then finally gives me a value of 10 amps, which is I right here.